Could one of our most fundamental beliefs about the universe be completely wrong? You've probably heard that the universe is expanding, faster than our current theories can explain, and that dark energy is thought to be the mysterious force driving this acceleration. But physicist Lucas Lombriser is challenging that idea with a bold new theory: the universe isn't expanding at all. According to him, what we perceive as expansion is merely an illusion, and the universe is actually flat and static. So what evidence backs this provocative claim? Could we really be so mistaken about something so essential? Stick with us to the end as we explore this fascinating possibility. Our understanding of the universe has undergone dramatic shifts over time. Just about a century ago, even brilliant minds like Albert Einstein believed the cosmos was static and unchanging. Back then, it was widely assumed that the Milky Way was the only galaxy in existence. That belief, however, was about to be upended, thanks to Edwin Hubble. Driven by curiosity about mysterious spiral nebulae observed in the night sky, Hubble began a groundbreaking investigation. When he studied a pulsating star within one of these nebulae, he realized it was far too distant to be part of the Milky Way. This discovery marked a turning point. Hubble soon concluded that these so-called nebulae weren't clouds within our galaxy, they were entire galaxies themselves. After the boundaries of the known universe rapidly expanded into uncharted territory, Hubble turned his attention to measuring the redshifts of these distant galaxies, categorizing them by distance, size, shape, and brightness. In the process, he observed a striking pattern: the farther a galaxy is from us, the greater its redshift, meaning it's moving away from us faster. This relationship between redshift and distance could be defined by a constant, leading Hubble to a groundbreaking conclusion: the universe is expanding. At the time, it was a revolutionary idea, but today it's a fundamental principle of astronomy and a key to understanding the origins of the cosmos. If the universe is constantly expanding, then logically, rewinding time would reveal that it was once much smaller, compressed into an incredibly tiny point. We now call this point the original singularity, the origin from which space, time, and matter simultaneously burst forth in the event known as the Big Bang. For a long time, this explanation seemed solid. Scientists had uncovered evidence of the universe's expansion and could trace it all the way back to that singular beginning. But, as always, the cosmos had more surprises in store. In the 1990s, astronomers made a discovery that upended long-held assumptions. Instead of slowing down, the universe's expansion had actually been accelerating for the past 6 billion years. This was puzzling. Shouldn't gravity have been slowing everything down? What force could be strong enough to push against gravity itself? The answer, or at least the current best guess, was something entirely unexpected: a mysterious force dubbed dark energy. Yet, there's a major caveat when it comes to the force opposing gravity: we still don't know what dark energy actually is or how it functions. The James Webb Space Telescope has only deepened this mystery. Although we haven't directly observed dark energy, theoretical models suggest it makes up about 70% of the universe's total energy density and plays a crucial role in driving its expansion. Still, despite all the speculation around dark energy, the expansion of the cosmos remains shrouded in enormous uncertainty. The Webb telescope has uncovered findings that once again challenge the very foundations of our understanding of the universe. This is especially true for early galaxies that appear far too massive for having formed just a few 100 million years after the Big Bang. More recently, Webb has added new layers to the puzzle of cosmic expansion, particularly when it comes to a fundamental question: how fast is the universe really expanding? As mentioned earlier, the expansion rate of the universe is represented by what's called the Hubble constant. However, here's the issue: the predicted value of the Hubble constant based on theory doesn't align with our actual observations in space. According to the Standard Model, the value should be 67 km per second per megaparsec, but when we measure using supernovae, gravitational lenses, variable stars, and red giants, we find that the Hubble constant is actually 73 km per second per megaparsec. To check for potential errors in previous measurements, the James Webb Space Telescope revisited data from its predecessor, the Hubble Space Telescope, as part of new observations. Once again, these findings showed that the universe isn't behaving as expected. In fact, The most recent results suggest a Hubble constant of 72.6 km per second per megaparsec, and scientists are struggling to explain this significant discrepancy, well, with one possible exception. Physicist Lucas Lombriser from the University of Geneva has introduced a controversial theory suggesting that the cosmos may not actually be expanding, but rather remain static. Could the perceived expansion of the universe be nothing more than an illusion? What led Lombriser to propose such an unconventional idea? In his publication in Classical and Quantum Gravity, the lead author explains his hypothesis. In this work, we offer a fresh perspective on the universe and its unresolved mysteries by mathematically reformulating the physical laws that govern it. Lombriser argues that the observed redshift of distant cosmic structures could be attributed to the evolution of particle masses over time, such as the changes in protons and electrons. In the same vein, he introduces a revolutionary idea by replacing the traditional concept of the universe's expansion with a dynamic field that permeates spacetime. In this model, the particles of the universe emerge from and move within this field. Here, the cosmological constant is no longer tied to the expansion of the universe. Instead, it is determined by the mass of the field itself. Since the field experiences fluctuations, the cosmological constant fluctuates correspondingly. In an intriguing twist, the physicist's calculations revealed that the observed data on redshift aligned perfectly with this new theory. Reflecting on the implications of this breakthrough, he remarked, "I was surprised to discover that the issue of the cosmological constant seems to simply vanish in this fresh perspective on the cosmos." This perspective suggests that the fluctuations within the field offer a more accurate and consistent explanation of cosmic phenomena, effectively resolving a long-standing problem in cosmology. At the same time, the new approach appears to offer potential solutions to some of the most urgent and enigmatic questions in modern physics, including the elusive nature of dark energy and dark matter. Both of these concepts, though fundamental to our understanding of the cosmos, remain largely theoretical. Dark matter, for instance, was proposed to account for the unexplained movement of visible matter in galaxies and clusters, and scientists have hypothesized that it may make up about 5 times the amount of ordinary matter in the universe. However, dark matter is invisible to our instruments, as it does not interact with light or other forms of electromagnetic radiation, making it impossible to detect directly. One intriguing idea brought forward by Lombriser is that fluctuations in a broader, underlying field could mimic the behavior of an axion field. The term axion refers to hypothetical elementary particles that are electrically neutral and have zero spin, characteristics that make them potential candidates for dark matter. These axions, if they exist, could help explain the missing mass in the universe. Moreover, Lombriser suggests that these field fluctuations might hold the key to understanding dark energy as well. He proposes that the influence of dark energy could be attributed to the changing developmental trajectories of particle masses at later stages in the universe's evolution. This would imply that dark energy's effects arise not from a constant force, but from a more dynamic, evolving process tied to the fundamental nature of mass itself. The physicist argues that in the context of this research, there is no compelling reason to invoke the existence of dark energy. But how is the broader scientific community reacting to this unconventional perspective? Luz Angela Garcia, a researcher from the Universidad ECCI in Colombia, who wasn't directly involved in the study, expressed a strong interest in Lombriser's novel interpretation. She stated, "The work is incredibly intriguing and presents an unconventional solution to several long-standing problems in cosmology. It offers a potential resolution to the current tensions and contradictions in the field." But what does this mean in practical terms? Does it suggest that we might need to rewind a century and revisit the old notion that the universe is static and unchanging? Well, perhaps we should exercise some caution before jumping to conclusions. While Garcia acknowledges the significance of Lombriser's findings, she also calls for a healthy dose of skepticism. Specifically, she points out that the theoretical framework put forward by Lombriser includes components that are likely untestable with current observational techniques, at least not in the near future, due to the limitations of our technological capabilities. As a result, it seems we may need to wait some time before we can definitively determine whether Lombriser's proposed field actually exists and whether it behaves in the same way as the elusive axion. This uncertainty means that while the theory is compelling, much of it remains speculative until further advancements in observational technology are made.